of its workforce, in the competencies of its industry, in the heritage of its educational institutions. There is a pressing need, however, for collaboration and cooperation between industry and government and academia. But this is best worked out, I think, on a regional basis, where the challenge is better defined and of more manageable proportions. Industry depends on its surrounding infrastructure in many ways for supporting services. And chief amongst these services is the educational systems, which not only educates and trains the workforce, but also creates the new knowledge about which we've heard so much here. And as we move farther into the information age, industry's dependence on the universities will become even more acute in this respect. But it's at the state level that critical decisions regarding education and other services that are important to industry are actually made. Let's take a look at Massachusetts as an example of a state that's made a successful transition from an old turn-of-the-century industry that was dependent on textiles and shoes to a high-technology industry that's today focused on computers and electronics. This transition has occurred over a 30-year period that began sometime in the 1950s. And for the most part, as you look back on it, it was largely unplanned and unforeseen. It occurred largely as the result of a high concentration of technical education resources in Massachusetts. And these technical resources, in turn, attracted investments from the federal government in supporting R&D during the Cold War period of the 50s and the space race of the 60s, which only served to strengthen the leadership of the region's technical universities, in particular MIT. Just to illustrate, in 1960, Massachusetts, with only about 2.5 or 6% of the nation's population, produced 5.6% of the country's bachelor's degree graduates in electrical engineering, 10.7% of its master's degree graduates, and 11.6% of its PhDs. By 1983, Massachusetts had captured 10% of the U.S. computer-related employment, 9% of electronic component employment, and 9% of the measurement and control equipment employment in America. Massachusetts today ranks first amongst the 10 largest industrial states in the percentage of manufacturing employment in high-tech industries, about 35%. And interestingly, surrounding states in New England, New Hampshire, Vermont, Connecticut, Massachusetts rank respectively first through fourth in their percentage of total employment in high tech. This illustrates, I think, the spreading effect as employment gradually permeates the regions that are contiguous to the centers of this technical higher education. The close connection between industry and the universities in the region is dramatized by an MIT study which in recent years showed that 80% of the engineers that worked in Massachusetts companies received their last education in Massachusetts schools, and an astounding 94% in New England schools. And the close proximity of industry to technical universities will only become more important in the future, as the rapid pace of technological change requires continuous lifelong education to become a reality. One cannot overemphasize the importance of MIT in the development of the Massachusetts high technology industry. An MIT Sloan School study showed that 216 high technology companies in the Boston area, of these, 156 of them were born out of MIT departments and laboratories, including the most famous Digital Equipment Corporation. MIT is a magnet which draws top talent from around the world. While only about 9% of the residents of the citizens of Massachusetts attend 9% of MIT's undergraduates come from Massachusetts. 36% of the graduates remain in the region after graduation. And it's estimated today that about 10,000 MIT graduates live in Massachusetts. Many of them are heads of corporations. Others are professors and administrators in many of the technical universities. And this has earned the label for MIT, amongst many, as a teacher of teachers. A look at other electronic industry centers like California and Texas and New York reveals a very similar pattern to that of Massachusetts. These states, too, are top-ranking producers of electrical engineers, and they're well endowed with major research universities. But despite the success of the high-technology industry in Massachusetts, as late as the mid-1970s, the underlying driving force for the economy there was not well understood. And as a result of this, business, education, and government were going off in different directions, leaving the high technology industry in serious jeopardy. In Massachusetts at that time, personal taxes had risen to 20% above the national level, making it increasingly difficult to attract and retain the scarce engineers and technical managers that were required. Funding of public higher education in Massachusetts was near the lowest of the 50 states on a per capita basis. The output of colleges, the state colleges and universities in Massachusetts were very badly mismatched to the job market. State services were unresponsive to industry needs. And as a result of all of these things and others, Massachusetts earned the label of Taxachusetts, and many companies were beginning to look to greener pastures for their expansion. In 1977, a concerned group of high technology executives formed the Massachusetts High Technology Council to collectively search for solutions to these and other related problems. The High Technology Council played a major role in defining the future growth opportunities for the state, and in defining the conditions and the resources that would be required to exploit these opportunities. It analyzed the supply and demand profile of the technical workforce and quantified a large and growing gap in certain job categories. It defined the curricula requirements for many courses, particularly in electronics and computer programming and technicians and professionals alike. It took the lead in building a closer relationship with local universities and providing badly needed resources to help them solve their problems. It joined with a grassroots citizens group to lower the tax burden, not on corporations, but on individuals. Once the problems facing the high technology industry were known and understood not only by the government and educational leaders of the region, but also by the public at large, corrective action came with amazing speed. By 1983, only 6 years later, the tax burden on individuals had dropped below the national average. Spending budgets for higher education focused on job needs was growing again despite a severely austere budget in Massachusetts. The output of electrical engineering graduates had risen by 60% in just that period of time. Industry support for higher education was at record levels. Industry and universities were collaborating on a broad range of initiatives that would be important to the future long-term growth of the state. Just to mention a few of these was the initiation of the Massachusetts High Technology Park, based on $20 million of funding from state government. A microwave link was initiated to connect industry with university to facilitate communications. Career transition programs were established, model programs particularly for RIF teachers to provide a transition into the high technology industries. So in short, the business climate in Massachusetts is today riding a new high, as the unemployment dropped from the highest in the nation during the 1974-75 recession to amongst the lowest of the industrial states during the most recent recession. The benefits of success of the Massachusetts high technology industry go well beyond employment in the industry itself. A report by the Boston Federal Reserve Bank suggests that the expansion of the high technology industry had a direct multiplier effect on local business services such as advertising, public relations, data processing, management consulting, financial and legal services in numbers that were very impressive. The analysis also showed that there was almost a 1-to-1 ratio between jobs created in the office and computing machine sector and in those in the computer services sector. But even more important, we can view the high technology industry as the tool makers of the 80s and 90s. High-tech products like word processors and robots and computer-aided design and manufacturing equipment put the latest technology in the hands of workers in all segments of our economy, in mature industries and service industries and hospitals and universities and banks and government offices, workers everywhere to increase their productivity and their competitiveness. And while workers in our hospitals and insurance companies don't compete directly for jobs with the Japanese, they do very much compete indirectly in a way that's not maybe so obvious. For example, it's estimated that the cost of medical insurance translates into almost $500 for each car manufactured in Detroit. Higher service costs in education, hospitals, and insurance companies escalate wage demands and benefit costs in manufacturing. And as a result, increase the cost of our exported products. Fewer cars sold, for example, means not only fewer jobs in manufacturing, but also fewer service jobs as well. So considering that 80% of our workforce is engaged in non-manufacturing industries, perhaps the greatest impact of the high technology industry will ultimately be in boosting the productivity of our white-collar workers in the service industries and other areas of our economy. And there's ample evidence that high technology is already beginning to have a pervasive influence on the productivity of all segments of our economy. In 1982, 1/2 of the capital expenditure investments in America were for computers, communication equipment, and electronics of various sorts. This is up from just 25% 10 years ago. Now, not every region of the country, like Massachusetts, will flourish as manufacturers of computers and word processors and other high-tech tools. But every region can and must benefit from using this new high technology that's embodied in these products to boost their productivity and to alter the nature of its products and its services. The challenge will be for each region to determine how best to make this transition. In most cases, the answer will not be to abandon existing industries, but rather to build on them and out of them. We see this already happening in a unique way in various regions of the country. Detroit represents perhaps the most dramatic challenge, not only because the auto industry is so important to our national economy, but also because cars are a symbol of American manhood and prestige in many ways. And if we can win in Detroit, this is going to lend courage and hope that we can make this transition in other mature industries as well. The challenge in Detroit is not just innovation incorporating new technology to automate manufacturing, but also innovation in building new and more productive relationships between workers and managers. And it's indeed encouraging to see both of these things happening today with amazing speed. A major challenge also will be to infuse new knowledge and skills to the workforce to apply and operate and maintain these new machines that are based on this modern technology. As in Massachusetts, a turnaround in Michigan will require a collaborative effort between industry and universities of unprecedented scope to educate a new generation of workers while re-educating an older generation. The technology to apply computer-aided design and manufacturing equipment is going to have to be worked out in Detroit and Ann Arbor and Lansing, not in Boston and in Palo Alto. And this is beginning to happen. At the end of his term of office in 1980, the governor of Michigan got his legislature to create an Industrial Technology Institute, funded initially with $6 million of state money. ITI's work is focused on accelerating the adaptation of automated manufacturing technology to auto firm supplier companies, of which there are several thousand in Michigan alone. This institute is located adjacent to the University of Michigan in Ann Arbor, and is supported now by additional $40 million funding and grants and pledges from the Kellogg Foundation and another $9 million from the Dow Foundation. GMF Robotics, which is a joint venture a company with General Motors, already promises to be a leading, if not the leading, manufacturer of robots in America. And that's not just to meet their own needs or the needs of the companies in Detroit, but also for export throughout the world. And there's really no reason to believe their ability or their motivation to accomplish this goal, and thus to turn Detroit in this respect into another center of manufacture for high technology tools. The transition in Michigan can best be accomplished through local collaboration and cooperation by automobile manufacturers and their suppliers, sponsoring joint research and educational programs in local universities, by auto manufacturers and unions negotiating a new vision of productive relationships, by state governments supporting and encouraging the transitional processes, especially in education, that are required to succeed in an increasingly knowledge-intensive era. When we look at Massachusetts as well as Michigan, much has already been accomplished, but much more remains to be done. And one of the keys to success is better communications amongst the major players. This will take a significant commitment of time and effort from the leaders of industry, government, and education to understand in detail each other's problems and concerns and needs and mutual interdependencies. And I can speak from personal experience from my own case and others in Massachusetts that to make these efforts work takes a tremendous commitment of time and effort. And this task cannot be achieved by corporations acting singularly or by the CEOs delegating this task to people of lesser organizational scope and authority. It just takes a huge involvement and commitment that is uncharacteristic in many ways of American industry, steeped as it is in self-reliance and fearful of reprisals for collaborating with competitors. In large measure, the success of the High Technology Council in Massachusetts can be attributed to the involvement of corporate CEOs, collectively fashioning policies and goals that not only address their own corporate needs, but also the broader needs of the communities and the citizens of the state from which they draw their employees. This was not a broad coalition of industrialists and bankers and other businessmen, but rather it was a highly focused group of electronic and computer executives, in many cases arch competitors, but ones who shared common problems and common concerns. And by thoughtful analysis, this group was able to forge a consensus on the requirements for its continued success in Massachusetts, and then to effectively communicate this consensus so that others in the state could understand and respond appropriately. Natural partners for industry seeking to new ways to compete in the knowledge-intensive age are universities and institutions of higher education. In addition to industry leaders pulling together amongst themselves, there's also a very great opportunity for universities to exercise leadership in establishing centers of excellence that would promote collaboration and cooperation amongst companies having common interests. In many ways, these centers are not unlike the agricultural extension centers of the land-grant colleges that were so successful in the late 1800s and the early 1900s in educating farmers and in spreading the new mechanical technology that was important to that era. University centers of excellence linked to industry groups represents a powerful model to generate bottoms-up solutions to well-defined regional problems. By pooling industry resources to fund university-based research, these joint ventures minimize the duplication of costly research and make the results open for public consumption. They speed up the transfer of newly discovered knowledge into commercially viable products and processes. But even more importantly, these research partnerships provide a mechanism to merge the collective wisdom of industry and academia in setting the agenda in specific areas where basic research is needed. They establish a balance between market needs and technology seeds. They offer the breadth and the diversity to accommodate the wide-ranging interests of our many regions and our many industries. In short, they offer an alternative to a meaty-style centralized industrial policy by empowering a network of bottoms-up decentralized mini-meaties that are distributed across our vast nation to both formulate and implement a long-term agenda of basic industrial research. In this model, industry cannot do the job alone. State governments must play an active role in encouraging and supporting the processes of renewal and change, while the federal government can best contribute in a passive role by providing grants to match industry and state government sponsorship of university research, as well as tax credits and incentives to business also for this purpose. The transition in Massachusetts and the continuing adjustments there that are to the knowledge-intensive era that are going on today are following, in many ways, uncharted paths. But the transition is nonetheless occurring without the benefit of a national policy or an industrial policy. And I believe that in retrospect, when history is written, that the transition will occur in Michigan, and it too will occur without the benefit of these policies. It's local people talking to each other, solving local problems, understanding local opportunities. We don't need help from Washington to understand that we've got problems in Massachusetts in areas like New Bedford and Roxbury and Fall River. But if the local government and the local industry and educational leaders there are not concerned enough about these problems to seek out solutions, is it reasonable to assume that someone or some organization here in Washington will have the knowledge or the motivation to do a better job? The way Washington can help is to get its own house in order, with sound fiscal policies, with investments to encourage innovation and change. And again, as Congressman Zhao emphasized this morning, it's absolutely essential that Washington, as well as our state governments, also come to understand much better the generic processes by which renewal and change actually occur in our industries and in our economy. and that they then remove the obstacles and grease the skids so that some good old-fashioned Yankee ingenuity can work its magic. Thank you.
We have some time for questions.
This is my mic, I'm just doing it.
Thank you very much.
Is that in the right place now? You should be able to move it where you like.
The next paper in this session is entitled A New Charter for Telecommunications, a subject very much of interest to us in the engineering profession these days, and perhaps to the general public at large. The paper will be presented by Dr. Ian Ross. Dr. Ross is the president of AT&T Bell Laboratories and is a member of its board of directors. He is also a member of the board of directors of other AT&T subsidiaries, including Sandia Laboratories in Albuquerque, New Mexico. He received his PhD degree from Cambridge University in England in 1952. Dr. Ross is a fellow of the IEEE and was also honored by the Institute with the Morris Liebman Award in 1963. Dr. Ross.
Thank you, Mr. Probst. I'm accustomed at this time of day to talking to an audience that's beginning to feel a little weary. It's the first time I've dealt with a microphone that is drooping. Is it working indeed? It is or it isn't? Well, I'll yell into it. I'm very pleased to be talking today about the new charter in telecommunications, because indeed, I think we have a new charter in telecommunications, and I'd like to describe to you what I think it is. And I think it's a two-pronged charter, one based on legal issues and the other based on technology issues. And following that, I'd like to talk to you about what I see the stakes to be with this new charter and what are the challenges that we all have in dealing with those stakes. Well, let's look at the legal charter, and that legal charter came clearly out of the recent divestiture of the Bell system. And one has to ask, why did we have this divestiture in this country? And to my mind, it is a simple result of a basic principle, and that is that in most enterprises, competition and regulation just don't mix. And when you have those together, you have an unstable situation looking for an eventual solution. Now, in this society of ours, competition is the rule, and regulation is the exception. That wherever possible, we use competition to control the supply of products and services to our people. And only where that cannot happen, we use regulation as a substitute for competition to ensure that pricing is fair and that service is proper and of high quality. Now, as you probably know, originally, way back in telecommunications, we had competition, but it led to installers in fisticuffs fighting for the provision of service to residents in their own backyards, and this was not satisfactory. And what was worked out years ago was a regulation of the telecommunications business in this country. And it worked very well indeed. But over about the last 15 years, we began as a nation to introduce competition into the telecommunications business. We introduced it maybe first in the terminal business, and then more recently in the long-haul transmission business. And that's when we all began to learn or relearn that competition and regulation just don't mix. Because what we found was the regulators properly trying to guard against the cross-subsidy from the regulated business into the competitive business, which they considered to be anti-competitive. At the same time, they were trying to maintain the cross-subsidies that were considered to have social values. And what you end up then is that new businesses who enter the arena do so at the peril that the regulatory environment that brought them in might change after they come in. And the existing businesses find themselves hamstrung by the ever-changing regulatory environment. So what is the solution to that? Well, you come to a simple solution, whether you like it or not, and that is that you separate the natural monopoly, which in our case was considered to be the local exchange service, from the inter-exchange and terminal business, which was considered properly to be competitive. And having done this, then in the remaining competitive part of the business, you no longer worry about cross-subsidies, you no longer worry about customers making inappropriate decisions because of artificial pricing. A good, straightforward solution to a problem. And that has taken place, and the business has been split. It was split on January 1. But let me leave you with a warning. And the warning is that this solution will not work well until the competitive component is fully competitive. Until we have an even-handed regulation of the competitive side of the business. Now, if you look at the long-haul transmission business, and you look at the terminal business, if you question for a moment that it's competitive, then read your newspapers and see what's being advertised, both in terminals and both in the long-haul transmission business. Yet, if you also look at it, I think you'll find that the regulation of both of those parts of their business is not yet totally even-handed. And I'll repeat then that for the nation to reap the full benefit, then we really must finish the job. For it is still true that in the long run, competition and regulation don't mix. Now, what about the second prong to this, the technological prong? I think in a real sense, the technology has driven the legal and regulatory issues. Starting with World War II, or just after World War II, and increasingly in the 60s and 70s, and particularly as the semiconductor business went through its very, very dramatic progress, the technology that underlies telecommunications systems and services became ever more widely available. And thus it was possible for competitors to move into that business without an extremely large initial upfront investment. And that, I believe, is what made it possible and therefore presumably desirable to bring competition into that part of the business. Now today, this same technology that underlies the business is moving very, very rapidly. It's moving so rapidly that even those in the business are having trouble keeping up with it. And here I'm referring to the microelectronics, the software that goes with it, and more recently to the progress in the photonic technologies, the light wave technologies. And let me talk about just some of these briefly. Much of this will be not new to you. But look at the microelectronics progress, the silicon components on a chip of silicon. That business over 2 decades has been progressing exponentially. In that first decade, doubling the number of components on a chip of silicon every year. And in the last decade, and continuing through today, doubling the number of components on a chip of silicon about every 18 months. Very, very dramatic progress for any human endeavor. And as a result of that, during that period, the cost of a single component or equivalent function has come down by at least a factor of 1,000. And as you know today, we are now manufacturing in this nation silicon memory with 256K memory slots and about 600,000 equivalent components. And there's no question that the design of a manufacturable 1 million bit, 1 million component chip is at hand. And what has it meant? Apart from memory, it means that the microprocessor chip of today has already challenged in capability, surpassed in capability, the mainframe computer of 15 years ago, and is challenging the capability of the today's mini computer. Now, where is this heading? As I say, we are continuing this progress at about a rate of doubling every 18 months. And my expectation is that we will continue to do that, and I see nothing in the physics or the chemistry that will limit that until we reach at least 100 million components on a chip of silicon about a square centimeter in size. And that we should be able to do in about 10 years. And even further, I don't see any reason that by the end of the century we should not have 1 billion components on a chip of silicon about the size of a postage stamp. And by the way, that chip of silicon may then cost less than the cost of mailing a letter across the nation if we at that time still choose to communicate by those means. Now, if you believe what I'm saying, if you believe that another 20 years of progress at this rate is ahead of us, then what we are saying is that the microelectronics business is only at the halfway point. We have another 2 decades following the first 2 decades, and that the dramatic impact on society that we've already seen, still the same amount of it at least is yet to come. Now, there's similar progress going on in photonics, the business of transmitting information by using the photon rather than the electron. And if you take there as an index of performance the maximum bit rate, the maximum information rate you can transmit, times the maximum distance you can transmit it without having to repeat, without having to amplify, without having to reprocess, that index of performance for light wave communications is doubling every year. Another one of these remarkable exponential progress. And today the record for transmission is to send 1 billion bits per second over